So a little overview of what we're going to cover today. First, we're going to have a look at machine learning in the energy industry. I'm an energy engineer, so that's why I'm speaking to you today. We'll then have a look at what is reinforcement learning, and then finally we'll have a look at one of the seminal papers in reinforcement learning. And that's DeepMind's 2013 paper, where they taught a reinforcement learning algorithm to play Atari games. Right, so machine learning in the energy industry. I'm an energy engineer, I'm not a data scientist. I've spent the last 3 months doing a data science bootcamp in Berlin, so I have some understanding and gaining it all the time. But why am I interested in machine learning? I'm an energy engineer. The reason is that machine learning is super exciting. The results that people are getting are superhuman. And in the energy industry, we obviously have this massive challenge of decarbonization, and to get superhuman performance, whether it's an operation or design or any aspect, is something that we really need. So that's why I'm interested in machine learning, being an energy engineer. So some of the examples of machine learning in the energy industry. One of the most famous ones is Google's optimization of their data centers. 15% improvement in efficiency. And the reason that this is super exciting, there's two reasons. One, Google's data centers would have already been hyper optimized, and they let machine learning have a crack at it, and it managed to squeeze even more efficiency out of the plant. So this is the superhuman performance that I'm talking about. Reinforcement learning, for me, is the most exciting part of machine learning in the energy industry. And the reason is that it gives us an opportunity to operate energy systems at superhuman levels of performance. And that's something that I'm really actually passionate about achieving. Right, so we have this thing in the energy industry called the operator's dilemma. And essentially, when you have an energy system, whether it's an international electric grid or a residential heating system you have in your house, there's decisions to make on how to operate that system. And it's very hard to do. There's a lot of variables that change from day to day, even hour to hour. And it makes understanding how to optimally dispatch your assets very difficult. So reinforcement learning can solve this problem for us in the energy industry. Reinforcement learning can operate our energy systems for us. So why reinforcement learning? One benefit is the automated control. You don't need machine learning to get automated control, but it's a benefit that comes along with it. And the other thing that's super exciting for me is that you have a model that interacts with the plant directly. You don't need to build an abstract model like linear programming, for example, to sort of estimate and abstract the site. You can actually let the algorithm that's controlling the plant experience and understand and interact with the plant directly, which is super exciting. And then some of the challenges that we have, data digitization is still a challenge in the energy industry. We're quite far behind. And then also it's a paradigm shift. A lot of machine learning, especially reinforcement learning with actual physical systems, it's a bit of a paradigm shift for a lot of people. And this is just an example of how we can use reinforcement learning in the energy industry. It's quite simple. It's just charging a battery, essentially arbitrage of price. So you can see here that as the electricity price is low, the model charges the battery, and then when the price starts to peak, it discharges and essentially makes some money off that. So this is kind of one example of how we could apply reinforcement learning to operate an energy asset, a battery. Right, so what is reinforcement learning? Some of you might not be familiar with the topic, and even machine learning in general. So machine learning can be roughly split up into three broad categories based on the kind of feedback that's available to the learner. So supervised learning, you get a big data set and you try to learn some patterns from that using machine learning techniques. Now reinforcement learning is quite different because in reinforcement learning you don't have a data set. All you have is a system that you want to control and a learner that can learn how to do that. And the way that it does that is by taking actions, generating data from those actions, and then learning from that data. So reinforcement learning is kind of a step above, or not a step above, but an additional task where we have to actually generate our data set for ourselves. So what is reinforcement learning? Reinforcement learning is learning through action. It's learning by taking an action, getting some feedback, and then understanding, which action to take next. A good analogy of reinforcement learning with supervised learning is the game of chess. So if you're going to learn the game of chess in a supervised manner, what you would do is you would sit down with a textbook of moves of grandmasters, you would study those moves and try to get an understanding of how to play chess. The reinforcement learning way to play chess will be to sit down at a chessboard and play yourself. That's kind of the difference between the two methods of learning. So this is essentially the reinforcement learning problem. You have an agent and an environment. These are the two systems that you have in reinforcement learning. So the agent is the learner, the agent is also the decision maker. So it takes an action, the environment responds to that action. The environment then sends a signal to the agent, the state, which essentially is, which we'll go into in a bit, and then a reward signal. And what the agent is trying to do is to maximize that reward signal, not just instantaneously, but over the course of the episode or into infinity if it's an infinite problem. So key concepts in reinforcement learning. The agent and the environment, as I just covered. So the goal of the agent is to maximize total reward, and it does this by following a certain policy. So policy is just a rules by which to choose an action. So you could have a policy of always choosing randomly, or you could have a policy of always choosing a specific action. But the policy that we're most interested in is the optimal policy, the policy that maximizes this total reward. So we have this signal state that's sent from the environment to the agent. And state is a flexible concept. So it can be anything that you think will help your agent to learn. For a reinforcement learning problem, there's different ways to design the state signal. It's as a modeler or as an engineer, it's one of the ways that you can influence the reinforcement learning algorithm. The next signal that we have sent from the environment to the agent is the reward signal, and this is the signal that the agent is looking to maximize. And it's a scalar signal per time step. And the reward signal has two properties that make reinforcement learning a challenge. One is that the reward signal can often be delayed. So again, thinking about our game of chess, you spend your whole time playing chess, getting absolutely no feedback at all, and then at the end you get a win or a loss. So you have very little information to actually learn from there. You don't know if a move that you made at move 10 is the reason that you won, or if the move that you made at move 10 was actually the wrong move to make. So this is a challenge for a reinforcement learning system to think, which of my actions over the episode is actually leading to this reward that we got. And the other nature of the reward signal is that it's often sparse. So by sparse, what we mean is just, again, going back to the chess analogy, you only get feedback, one bit of feedback. You don't get feedback every time step, like you do with supervised learning, where for every sample that you have a target, you have some sort of feedback going to the learner. A lot of the time in reinforcement learning, it's just complete silence. There's nothing to help the model learn. Right, a lot of that I've just covered. One dilemma that's very interesting in reinforcement learning is the exploration versus exploitation dilemma. And essentially this is, do you keep doing what you think is optimal, or do you take a chance and explore? Do you always go to the restaurant that you think is the best in London, or do you try a different restaurant randomly? That's essentially the exploration versus exploitation dilemma. Another thing that's very interesting about reinforcement learning is the data set that you generate is highly correlated. So the state sequences that you go through are correlated with each other. There's a relationship there. The other thing that's very interesting is that as you learn, the data set that you have, the distribution of that data set changes. Because as you learn, you're taking different actions, so you're essentially exploring a different part of your data set. So it's very difficult for a supervised learning method to deal with that. You usually want to have data that is not correlated and a distribution that represents the data set that you're interested in. In reinforcement learning, we have to deal with, as we learn, that distribution is changing. So that's one of the challenges in reinforcement learning. Right, so we have this concept of reward, which is instantaneous, and we abstract that slightly to a concept of return. So return is just the total reward over the whole episode. And there are some equations in this presentation, so apologies for that. But essentially what the reward is, just the reward for the next time step, and then we have a discount factor, and then the reward for the next time step. And so why do we discount? Well, one of the reasons that we discount is that the future can be inherently uncertain. You could have a stochastic process in your environment that means even if you act absolutely correctly, you might not get the reward that you deserve or expect. So that's one of the reasons that we kind of peg back the future rewards. Another reason for discounting is that it actually matches the way that human beings think. Human beings prefer to get reward now than later. It's called hyperbolic discounting. And the other interesting reason or concept of discounting is that we also find that in finance with the time value of money concept. This is where if you have £1,000 today, that's worth more to you than £1,000 in a year's time, because in that year's time we could invest that money, make more money essentially. So these are kind of some of the ideas or concepts that have slipped into reinforcement learning. So we have the concept of return, which is the total value, the total reward over the length of the episode. We then continue our abstraction into something we call value functions. Now, value functions are very crucial for the type of reinforcement learning that we're going to cover today. Essentially, it is the fundamental thing that you're trying to learn. You're trying to learn these functions. So there's two ways that we can approximate the value function. We can have it as a function of just the state, or we can have the action value function where it's a function of the state and the action. So for the value function, I'm in state S. How much is that worth to me? How much is my reward, expected reward in the future? And every value function is specific to a certain policy. So if you had a policy of always acting randomly, your value function is going to be quite different from the optimal value function. So I just want to stay on this concept for a little bit longer. The value function can be quite usefully thought of as an oracle or something that predicts the future. Essentially it's this function tells you this is what's going to happen in the future if you take this action, when you're in this state. It's a very useful concept to get an understanding of what a value function is. So we have this value function. How can we approximate it? Well, there's a number of different methods that we can use. We can use a lookup table, a linear function, or a non-linear function, such as a neural network, which gets everyone excited. There's a number of reasons why you would want to use a function rather than a lookup table. Often you can represent the information with less parameters than you would need inputs into a lookup table. So I think for really serious reinforcement learning, no one will really use a lookup table. And neural networks are useful because you can learn that non-linearity that exists in most environments. Right, so how would the optimal value function help us to act? What would we do with this function if we did have it? Well, what we would do is we would just evaluate that function for every different action that we had, and then we would select the action that had the highest result. So the action that the value function is telling us will get us the most reward, that's the action that we select. But the thing is, we don't have this value function. We start out with a neural network with random weights. We have no way to get it without doing some reinforcement learning to actually learn and improve our approximation of the value function so that we have something that will help us to optimally act. So again, returning to our concept of the oracle, what would we do if we had an oracle? We have our oracle that we can ask, what's the value of being in this state and taking this action? And we have our neural network. So we would just train our neural network to minimize the difference between the oracle estimate and what our neural network was giving us with the set of weights that we had at the moment. But we don't have an oracle. We don't have this information about what the true value of a state action is. So this is where Q-learning comes in. Now Q-learning relies on this association between the current state and the next state. So if I'm in state S, the value of being in this state is quite simply equal to the reward that I get after I leave that state, and then however much return I expect going forward. So this is the intuition that Q-learning relies on, is that we estimate the value of our current state action being equal to the reward that we saw, and then whatever we think the value is for the next state. So how do we create our estimate? Well, what we do is that as we step through the environment, as we experience states, taking an action, getting a reward signal, and then understanding which state we end up in next, we can then train our neural network using that memory by bootstrapping off this function that we already have. So this symbol theta here is the weights of the network. And what this is saying is that whatever my network is giving me, even if it's nowhere near what the actual optimal value function is, let's just use that to estimate the value of the state that I'm in. And let's use that to train our neural network to better approximate the actual optimal value function. So this is just a summary, sort of a demonstration of this is how Q-learning is working compared with our oracle. We just substitute in our oracle estimate with this bootstrapped estimate of the value of our state, using the same function. So you can see here that we are improving our function, weights theta I plus 1, using our old function, theta I. Right, so I just want to take another step to appreciate how magical this value function really is. You know, magical for two reasons, I think. The first reason, that it exists at all. That there is a function that can predict the future in terms of the thing that you really care about, your reward signal, you know, whatever it is for your given environment. The fact that that exists is quite crazy. And then the second reason is quite crazy is that we can improve our estimate of this value function using our own estimate of the value function. You know, we can start out with a neural network with random weights that's giving us absolute garbage. And by stepping through the environment and by training and training, we actually end up with an optimal value function that is quite a good representation of you know, reality. So this is just a summary slide, more for you to go over later. If you're thinking about doing this, these are kind of some of the parameters or things as a modeler that you need to choose and learn and take forward. Right, so the third part of this presentation today is having a look at one of the seminal papers in reinforcement learning back in 2013. And just to give you guys an understanding of how important this paper was, DeepMind, which are based in London, were bought by Google in 2014, I think for roughly £500 million. And this is for a company with no products, no customers, few employees. So that really gives you an idea of how significant this paper was, how much Google valued it. Right. So why was it so significant? What was so important about this paper? Well, one reason is that it's an example of end-to-end deep reinforcement learning. So what do I mean by end-to-end? Well, all that this model got as an input was the computer screen. It didn't get any sort of, there was no feature engineering to tell the algorithm, you know, this is a ship, this is an enemy, this is a ball, you know, for whatever game it was. All that the model got was the actual pixels that were appearing on the screen. And this is riding off the coattails of advances in convolutional neural networks and stuff that have allowed them to do this. The other thing that's really significant about this paper, and I think the reason that DeepMind were quite excited about it, is that it was the ability of the algorithm to generalize. So in this version of the paper, I think they played 7 different games, all and 3 at superhuman performance. With exactly the same model. You know, no hyperparameters were tweaked, except for one, I think, but that was just to do with the way that the images appeared on the screen. But actually, it's the same network, it's the same hyperparameters, can be used to learn a game just from looking at the screen, you know, with no sort of understanding that this is even a game. You know, it just sees the numbers that represent the pixels. And it's been called in hindsight the first step towards a general artificial intelligence. Whatever that means. So how did they formulate the playing Atari games as a reinforcement learning problem? So Atari is a games console, and what they did is they took the state, they took the last 4 screens as the state. So again, this helps to illuminate the idea that the state is a flexible concept. You know, they could have taken 5 or 6 screens. You know, they designed that into the algorithm. The other interesting thing that they did is they clipped the reward. So the reward for these games is the score that you get for doing, you know, actions that the game wants you to do, but they actually clipped that from -1 to +1. You know, even if the score was +20, they clipped that down to +1. And this is just to get the algorithm to be able to generalize better. And they were learning Q here, the action value function. So this is the algorithm that they used, and hopefully now we can start to understand a little bit of this. So the first red box is how they dealt with the exploration versus exploitation dilemma. So what they did was some small probability epsilon, which was actually decayed from 1 to, I think, 0.1 over the course of the episode. With some small probability, they just take a random action. You know, they just explore the environment. They just kind of see, you know, let's go left and see what happens. Elsewise, they act according to their value function at the time. You know, they take the maximum across the value of all the actions that they have for the state that they're in. The second red box, this is how they're improving their value function estimate. This is how they're training the neural network using Q-learning. And then the third box, again, that's the loss function they were using. So how did they approximate the value function? So because they wanted to do end-to-end reinforcement learning, they had a convolutional neural network, 2 layers of convolution. One of the things that's quite interesting about this is that they didn't use max pooling after the convolution layers. And the reason for that is that max pooling essentially gives you translation invariance. You lose information about where an object is on the image. And this is actually why it's used in image classification, because you want to identify a feature that's anywhere. But for reinforcement learning, the information about where an object is actually very important. So that's why they don't do max pooling here. And also there's 2 network structures given here. They did a paper in 2013 and then an update in 2015 where they added on, another convolutional layer, and I think increased the size of the first 2 layers. I don't know how that's got in there. Okay, so visualizing our value function. So this kind of helps to demonstrate and understand what the value function actually represents. So we have this game called Sequest, where I guess the goal is to destroy enemies using your submarine. So we end up in state A, and we see that the value function has just started to peak up when we're in A. And why is that? Well, if you look at the left of screen A, you'll see that an enemy is just starting to appear. So what our value function is telling us that, okay, maybe there's some reward here. I'm starting to value the future slightly higher because of what I'm seeing now. We then transition to state B, and what our submarine has done is that it's fired a rocket and it's just about to destroy an enemy. So our value function has peaked up even higher. What our value function is telling us now is that I expect some reward in the future. And then we see after that we destroy that enemy and go to screen C. We see that the score has increased from 40 to 60, so we have got some more reward, like the value function was saying. But also now our value function is saying, well, you know, I'm not as excited about the future now. We've got that reward, you know, and we kind of end up in a position where we were before we were in screen A. Right, so part of the reason for this talk is to get people excited about reinforcement learning. So these are some of the resources that I've used to learn the small amount that I do know about reinforcement learning. The first one is such a fantastic resource. David Silver is one of the lead programmers at DeepMind. Amazing teacher, really wonderful to have that. But one of the ways that I would recommend learning reinforcement learning is to go towards OpenAI Gym, because what they do is they supply a whole bunch of environments for you to use your reinforcement learning algorithm with. So you can learn reinforcement learning by doing it yourself, which is the reinforcement learning way to learn. And then finally, this is a project that I've been working on. It's reinforcement learning for energy systems. So what it is a Q learner for the agent, and then also an energy environment for that model to learn from. So this is something that I'm kind of developing in my own time to sort of demonstrate the concepts, demonstrate that it works, try to get an understanding of, you know, what works for different energy systems. But it's the first step on a long journey, you know, and that's something I really want to emphasize. I actually really have a passion and a vision for this stuff actually working, because when I was working as an energy engineer, I was very frustrated by these energy systems that aren't controlled well. A lot of our energy systems are not achieving what they should be. So to have a method like this that can have us operating them at superhuman levels of performance, super exciting. And thank you. That's my talk.